Hello and welcome to this course on working with data in Android. As an aspiring developer, you will need to be able to demonstrate a working knowledge of how Android applications communicate over the web. This course will help you advance your app development skills by introducing you to Android asynchronous programming techniques. You'll also get to experience concepts and practices of the industry standard Structured Query Language, or SQL, as you explore storing app data using a product called SQLite. A primary driver of app adoption is the ready availability of timely information. Perfectly functional apps will lose your interest if you cannot depend on them to instantly provide you with the data you need when you need it. Your data requirement might be very specific, such as how close your taxi is or when your food order will arrive. Or it might be more global, such as when you want to hear about current world events or to research the best deals for a new mobile device. To satisfy the user's data requirements in your apps, it's vital to understand how Android apps can store and access files not only on a device's storage, but also from external online sources. In this Working with Data in Android course, you will expand your programming knowledge so that you can engineer better solutions when your Android applications communicate over the web. To do data development work with Android, you should have an advanced working knowledge of programming fundamentals, be familiar with the concepts of UX and UI design, and be able to create user interfaces in Android Studio. To assist with your learning, you will view and work on development tasks for the fictitious restaurant Little Lemon, where you will encounter many real-world scenarios. With your newly upskilled Android knowledge, you will work through these scenarios, overcoming challenges and implementing solutions. As your skill set grows, you will focus on many Android data concepts and tools, explore why you need them and how they are used. In this course introduction, you may encounter some new terms. Don't worry if you don't fully understand all of them. During the course, you'll explore these concepts in more detail, along with the core skills required to implement the concepts in your app development with Android. This course consists of 5 weeks of learning. By the end of this course, you should have acquired the skills and knowledge with the necessary tools to complete the end-of-course final project. Let's break down the content you will cover in each week of this Working with Data in Android course. Week 1 is your chance to get to know RESTful API development. The acronym API is short for Application Programming Interface, and REST means Representational State Transfer. REST provides guidelines that outline best practices for working with an API. After your studies this week, you will be able to explain different HTTP methods, status codes, and responses, identify the key characteristics, benefits, and uses of REST API, its states, and its resources, create routes with the correct naming conventions, explain the principles of authentication in a REST API, differentiate between authentication and authorization, and explain the API request lifecycle. Week 2 practices applying asynchronous programming techniques to query REST APIs and handle their responses using Kotlin and Android. You will advance your skills during this week to be able to explain concurrency in Kotlin, apply Kotlin coroutines in Android applications, and apply different concurrency patterns. Week 3 covers data in databases and accessing it using Structured Query Language, or SQL. After successfully completing this week, you will be able to explain what a database is and what its general uses are, explain how data is related in a database, differentiate between types of databases, and apply the syntax rules of SQL to use common SQL commands. In Week 4, you'll work with SQLite in Android. After successfully completing this week, you will be able to store simple data in Android using shared preferences, set up and query a SQLite database in Android, and connect data to app state. In this final week of the course, you will combine the concepts and skills gained from this course to complete the final app development project. The practical project work involves filtering and sorting an app's food menu and displaying it using SQLite. In addition, you'll get to reflect on the next steps in your learning journey. The Working with Data in Android course introduces you to many software engineering concepts to help you to better manage data in your Android apps. The important success factors for an app are not just about it looking well and functioning without error. They also include how well the app can deliver content to the user. Your programming approach to delivering content is based around creating and managing data solutions because these are vital components that ensure a successful app. I look forward to helping you advance your programming skills to the next level. Wishing you all the best on your Android learning journey.
By now, you know that HTTP stands for Hypertext Transfer Protocol, and that it's one of the most widely used communication protocols for transferring data across the Internet. Let's briefly refresh your memory of HTTP and HTTPS before diving into more complex topics. In this video, you will learn about how HTTP and HTTPS work, HTTP methods, HTTP requests and responses, and finally, HTTP status codes. When you browse web pages, view images, or submit a form, your data is transmitted using HTTP or a secured version of it, which is called HTTPS. But how does that transmission work for HTTP and HTTPS respectively? Communicating over HTTP requires at least two parts: the client, who requests some information, and the server who responds to this request and serves the content. HTTPS is the secured version of HTTP, which makes it better suited to instances where security is a concern. But let's find out how this works. With HTTPS, the client's computer encrypts data before it starts its journey to the server. The server then decrypts this client-side data and processes it. But the web server also encrypts the response data and sends the encrypted content back to your browser. Your browser then decrypts the response and displays it. Since the content is encrypted, it is more secure and very difficult to steal or retrieve information from it. For submitting sensitive data, like credit card information, it is always preferable to use HTTPS to make sure the data is secure. Now, let's move on to some common HTTP methods. HTTP methods are also called HTTP verbs. There are 5 methods commonly used when accessing content over HTTP. They are GET, which retrieves a resource; POST, used to send data to the server and then create a record; PUT, which updates the whole resource; PATCH, which you use to partially update a resource; and DELETE, which deletes a resource. Next are HTTP requests, which contain different types of information that a user's browser sends as encoded data. A typical HTTP request includes the following: HTTP version type, for example 1.1 or 2.0, URL or path, HTTP method, HTTP request headers, and an optional HTTP body. But what are the HTTP request headers and body again? Well, when you submit a form, like your username and password to sign into a website, that data is passed to the web server as the HTTP body as either a raw JSON string or a form URL encoded string. HTTP headers, on the other hand, are a core part of every HTTP request and may contain extra information that helps the server make some decisions on how to present the content. Examples of HTTP request headers are cookies, user agents, and referrers. After an HTTP request comes the HTTP response, which consists of information that the browser uses to properly display the content in the response body. The response contains the resource that was requested, and it also contains information like the length of the content type, and headers like cookies. It also contains e-tags, the time when the content was last modified, and finally, the response also contains some special numerical codes called HTTP status codes. You've surely seen these HTTP status codes, but you might not have known what they are for. Well, they are not really messages addressed to you, the user. They actually provide extra information to your browser about the resource. For example, if everything is okay, the server sends 200. You will not be aware of this because it doesn't even display in your browser. Or, if the requested content can't be found, the server responds with the 404 error code, which usually displays in the browser because there is nothing else to show. Here is a range of error codes and their meanings. 100 to 199 are used for informational messages. The codes from 200 to 299 are successful responses. 300 to 399 provides redirection information. 400 to 499 are client error responses, and 500 to 599 are server error codes. Server errors are usually raised when the server-side code lacks proper error checks in the code, configuration mismatch, incorrect package dependencies, and so on. The client-side errors usually occur when the client makes a bad API request with insufficient information in the request body, or when the client requests a resource that is not present on the server. But take note that sometimes the same status codes can convey different messages in different contexts. For example, a 200 status code for a GET request means the content was found. The same 200 code for a PUT request means that the data transmission and update process was successful. Similarly, for a delete request, this 200 status code means that the resource was successfully deleted. Some of the most used status codes are 200 and 201, 303 and 304, 400, 401, 403 and 404, as well as 500. You will learn more about what these status codes mean as you move through the course. And that brings you to the end of this HTTP recap video that refreshed your memory about HTTPS, HTTP methods, requests, responses, and status codes. These are the fundamental concepts that you will use to develop sustainable and manageable APIs. Now that you've had a refresher on HTTP and HTTPS, you are ready to learn about REST APIs. But first, you need to know what is REST. In other words, what makes the APIs RESTful? An API, or Application Programming Interface, is a gateway to back-end data. It allows you to easily access and modify this data. And REST is an architectural style for designing APIs for your project. It is hugely popular among developers because it's much easier to develop and implement than other architectural styles. What works in your favor is that the learning curve isn't steep and you can create production-ready APIs in a short time. But let's not jump too far ahead. You're not quite creating APIs yet. Rather, you are first learning about the basics of REST APIs. REST APIs provide an easy way for you to communicate with the server and access the data that powers your application. But an API is only RESTful if it complies with certain constraints. Let's examine them. It must have client-server architecture, a REST API is always stateless, and it should be cacheable. It should be layered, have a uniform interface, and it might also include code on demand, but this is optional. Let's explore each in more detail. The API should use client-server architecture. There should be a server that is serving the resources, and there should be a client who consumes them. A REST API is stateless. This means that the server does not contain any state of the API client who is making the call, so it cannot identify who is making the request or what their previously requested data was without proper user information. In fact, the state is only saved on the client machine, not on the server, and this influences what you should include in your API's endpoints or URL paths, but more on this later. The API should also be cacheable. This means that responses can be saved by a web browser or a server or any system. This caching process can help to reduce the server load by using the API result from the cache, instead of making an actual request to the server every time. Layered means that the entire system architecture can be split or decoupled into multiple layers, and you should be able to add or remove a layer at any time. The following diagram will make this layering more understandable. Layers of a RESTful API system could include a firewall, load balancer, a web server, and a database. Let's move on to the constraint of having a uniform interface. This may sound a little confusing at this point, but it means that the system should offer a uniform communication system to access the resources. For example, there should be unique URLs for each resource. There should also be a unified way to modify or proceed further with a resource from the API result or representation in a standard XML or JSON format. Lastly, code on demand means that the API may deliver some business logic or code that the client can run to further improve the response result. To understand this code on demand feature, consider the following script tag that loads some JavaScript code from an API endpoint of the Little Lemon restaurant. Once loaded, this script can display any special menu items for that day. For now, these 6 constraints are just theoretical. Do not let them confuse you. Once you start developing your APIs, these terms will become clear to you. Next, let's focus on resources. Resources are a core part of every REST API, so it's important for you to become familiar with how APIs present resources. Say the Little Lemon restaurant has a mobile app, which can be used by customers and managers. Managers can use the app to get information about orders and customers, while the customers use this app to browse the menu and place orders. To support this, the app uses different APIs to fetch data from the server, and in each case, the resource type will be different. Let's explore a few examples. If a manager wants to see all orders, the app makes a call to the API little.lemon/orders and displays the result. The resource type in this case is a list of order objects. If a manager wants to view more specific information about a particular order, say the order with the ID 16, the app makes a call to the API little.lemon/orders/16. The resource type is the order object. To see who placed the order, the app makes an API call with an extra filter /customer. This retrieves all the details about the customer of that order. The resource type in this case is the customer object. Say the manager wants to look at what the menu items of order number 16 were. The app makes an API call that replaces /customer with /menu items. Only the menu items of order 16 will show in the result, and this time the resource type is the menu item object. Now, on the other hand, if the customer wants to browse the menu, the app uses another API, little.lemon/menu items. And although the resource type will also be the menu items object, the return will be all available menu items of the restaurant. But sometimes the resource type is the same, although the result can be filtered to be more specific. Let's explore a final API to unpack this. This time, the customer wants to browse food items from a specific category, say appetizers. The app will add $category appetizers. Notice that the endpoint is the same as the previous API, but it filters the output to only appetizers. For both cases, however, the resource is still menu item object. Now that you've explored a few examples of API resources, let's revisit the REST API constraint of statelessness. You need to keep in mind that the server always represents only what you ask for. It does not remember anything of what happened before. For instance, if the manager retrieves the information about order 16 and then wants to look at the menu items of order 16, you cannot just send a follow-up HTTP request to the endpoint /menu items, because this API will return all menu items and not just the menu items of order 16. The server does not remember that your earlier call was for a specific order. If you want to get the menu items for a specific order number, you need to explicitly supply that order number to the server as orders/16/menu items. In simple terms, this is what stateless means. The server cannot recognize the client automatically. API calls must include more information about the user, but you will learn more about this later in the course. In this video, you have learned how to create REST APIs by following some key constraints. You also learned about the core parts of REST APIs, like the resource types. These conventions will help you build APIs that are easy to use and maintain, but there is a lot more to learn on how to optimize your APIs. For instance, using the correct naming convention. But more on this in an upcoming video. By now, you know the importance of API endpoints and how they determine precisely what data the server will send to your app. But a well-designed endpoint also conveys valuable information about its purpose, which is helpful for developers and the project itself in the long run. Your REST API's Uniform Resource Identifier, or URI, is one of the first things that users will notice when a page loads. It is also called an endpoint or URL path. First impressions always make a big difference, and that is why naming conventions for APIs are important. This video will help you name your API endpoints for maximum clarity and impact. Let's get started. Say the Little Lemon restaurant menu app needs APIs to display all their orders. A suitable API endpoint is /orders spelled with a lowercase o and not orders spelled with an uppercase O. So, your API endpoint should always use lowercase letters and hyphens to separate multiple words. Using underscores or snake case, title case, or camel case to separate words is not optimal because it makes the names difficult to read and understand. There is an exception to the camel case rule, though. If your API accepts a variable, for example a user ID or order ID, you should always represent them in camel case and wrap them in curly braces. For example, if you want to create an API for a specific order, it should be /orders /open curly brace order ID with a capital I close curly brace. By adding /menu-items to the API endpoint, you can fetch the menu items for a specific order. Or you can fetch orders of a specific customer by changing the ID to customer ID wrapped in curly braces and adding /orders. Notice that the API endpoints contain two different variables, order ID and customer ID, and they are both denoted by wrapping them in curly braces and writing ID with a capital I. Also, always try to use clear, concise, and meaningful words in your API names to make them easy to read right away. Next up, the use of forward slashes. If your project has related objects, you should use forward slashes in your API URIs to indicate their hierarchical relationship. An example of such a hierarchy is, a customer can have orders with order items in a restaurant API project. Another example is, a library can have books with authors, so to get the author of a particular book, you can use the API endpoint library/books/ and then book ID wrapped in curly braces, and finally /author. Or, to get all books written by a particular author, you can use an ID for the author instead and add /books. Notice how the relationships between the customers and orders, the books, and the author are all indicated with the / in these API URIs. Another naming convention is that your API should always use a noun to indicate the resources it is dealing with. An API that returns a collection of books or a book should use the nouns books or books and book ID wrapped in curly braces. Similarly, to get the price of a book, you should use the nouns books, book ID, price. API endpoints with verbs like get all books or get user, user ID are examples of bad API names. That's because the resources in a REST API endpoint should be always represented with a noun and never with a verb. API endpoints such as users, user ID, delete, or orders, order ID, save are also wrong because they use HTTP requests as verbs to indicate the action the API performs. Remember, you should send an HTTP delete request to users, user ID to delete a user, and you should send an HTTP put or patch request to orders, order ID to update the order. Endpoints that use standard CRUD operation names such as create, read, update, or delete should be avoided for two reasons. The resources these endpoints represent should be nouns, and the appropriate HTTP requests like get, post, put, or delete should be used with those endpoints to perform the necessary manipulations. Something else to consider is whether file names should be used in APIs. The Restaurant API project can return API results as XML and JSON data. So the question is, can you design your endpoints as orders, order ID.json to get the JSON data, or perhaps orders, order ID.xml for XML data? No, you should never use a file name extension in your API. To solve this problem, you should accept the expected data format as a query string parameter. So, if you want the output in a JSON format, you can add $format $JSON to the API endpoint. And for XML, you can use $format $XML at the end. Similarly, to deliver a minified version or source version of a JavaScript file, you use API endpoints like /assets, /JS, jQuery/3.6.0/min or /assets/JS/moment/2.29.4/original. But what if you need to filter a collection or perform a search? For instance, the Little Lemon restaurant has many items on its menu, but you are only interested in appetizers. To filter the results, you should always accept the data as a query string parameter. In a URL, everything you send after a question mark is a query string. Remember, the API endpoint menu items returns all menu items. But to only get the appetizers, you should pass the category name to the endpoint as category =appetizer. Consequently, if you design APIs that can be filtered this way, other developers on your team will derive that to get a list of mains or desserts, they can change the endpoint to category =main or category =dessert. This is the beauty of a good and consistent API naming strategy. Another best practice is that when you share your API endpoints with your team or the public, you should never add a trailing slash to the end of the API endpoint. What this means is that API names that end with a /, like orders, order ID in curly braces, followed by a /, is bad practice. So is sports, basketball, teams, followed by another / at the end. Simply end the API without the / at the end. So, if you want to become a fluent backend developer, you need to pay attention to your endpoints and make sure you use well-designed and user-friendly APIs. Let's recap the best practices discussed in this video. Use lowercase URI formatting. Indicate hierarchical relationships with a /. Use nouns for resource names. Avoid file name extensions. Furthermore, use query parameters for data types and don't use a trailing slash. Finally, always follow a consistent naming strategy and standard API naming conventions. Well-chosen names for API endpoints can significantly improve an entire project by making it easier for other developers to use your APIs. And now you are well on your way to creating good API endpoint names. If you want to work quickly and efficiently as a developer, you need the right tools. For example, an intelligent code editor can help you develop more rapidly and become more competent. In this video, you will learn about a few command line and graphical tools that you can use to play around with your APIs. You will also explore a practical demonstration of how to test APIs in Insomnia. These tools are a cross-platform, so you can use them on Windows, macOS, and Linux. You will be using some of these tools, like Insomnia, throughout this course, so it's important to learn about them now. Let's get started. First is curl, a well-known tool for developers who want to make HTTP calls from the command line. It is available for all major operating systems, but it doesn't have a graphical tool. To use curl, simply open your PowerShell in Windows or the terminal in Linux or Mac OS, type curl and hit enter. Curl makes it easy to send HTTP GET requests. For example, simply add the API URI after curl. This command sends a HTTP GET request to Postman Echo, a service from Postman, to display the headers and request body sent to it. Pretty useful for testing API calls. It works slightly differently for a POST request. This time, add the request body using -d and the HTTP method name, which is POST, preceded by -x. The second tool is Postman, which has cross-platform desktop tools that make it easy to test and debug APIs. With an advanced graphical interface and a web version, Postman is a powerful tool for API development. With Postman, you spend less time fiddling with API details and more time building the perfect API. You can explore their website in the additional resources for more information and learning materials. Another important tool is the Insomnia REST client, a powerful REST API client used to store, organize, and execute REST API requests. Insomnia is free, cross-platform, and comes with a very user-friendly interface. You can download and install Insomnia for your operating system from the link provided in the additional resources at the end of this lesson. Note that there's only a desktop version for Insomnia. In the rest of this course, you will be using Insomnia to play and interact with the APIs you build. Let's examine how to use it. Insomnia is a great tool for playing with APIs. All requests in Insomnia will be saved in a request collection. To get started, click on the Create button in the top right corner and select Request Collection. Give it a name, like First Collection, and click on Create. Now you are inside an empty collection. To create your first API request, click on the plus icon on the left sidebar and select HTTP Request. You can also do this by pressing Command plus N on Mac OS or Control plus N in Windows and Linux. You can double-click on the default request name New Request and change the name to something more personal, like First Request. At the top of the middle section, where it says Get, you can click and select the type of HTTP method your request is going to be. Leave it as Get for now. In the text box next to it, write your API URL https://bin.org/get ? project equals Little Lemon. httpbin.org is a free service that allows you to experiment with different types of HTTP methods. When you call one of these APIs, it prints back what you sent to it. Now hit the Send button on the right, and you will see that http://bin has returned the same query argument you sent to it, which, in your case, was project is equal to Little Lemon. This time, let's try making a new HTTP post request. To do this, click on the plus icon in the left sidebar and select HTTP request. Once the request is created, double-click on its name and give it a new name, such as Second Request. Now click on the HTTP method drop-down and select Post, and this time add https://bin.org/post in the URL field. You already know that a HTTP post request accepts arguments as form data or JSON data. With Insomnia, you can easily input data for a post request by clicking on the Body tab and selecting Form URL encoded or JSON. Here in this argument window, you can finally lay out all your arguments in an easy-to-use and organized manner. On the left, you can write the argument name, and on the right, the value. Write project in the argument field and Little Lemon as the value. Now click on the Send button to display the output. You can create as many requests as you want and come back later to play with them anytime. In this video, you learned about great tools such as curl, Postman, and Insomnia that you can use to create and test your APIs. Creating a REST API is straightforward, but to make it robust, reliable, and perform well under loads, you need to spend time planning the architecture. And that's where this video comes in, because you will learn about REST's essential best practices that every API developer should know. First is KISS, which stands for Keep It Simple, Stupid. What this means is that you shouldn't try to perform too many tasks with one API. A single API should do one specific job and do it well. For example, for the Little Lemon project, the manager needs to update the item of the day, and you want to make this easier for him by creating a new API. One approach is to let the API determine what the previous item of the day was and to remove that status from the item. And then it has to randomly pick one item based on some criteria and set its status as the new item of the day. But this is asking the API to do too many things. And if you randomly pick an item, it might not actually be the most popular item that day, right? A better approach is to create only one API which updates the menu item. Now, when the manager updates the item of the day, a HTTP patch or put call is sent to the API to set the status of the previous item of the day to off. Say item 16 is the item of the day. The API for such a call would be menu items/16 with a HTTP request body with a status set to off. The manager then manually selects a new item of the day, which makes another API call to update its status. A put or patch request is sent to menu items /21 with a status parameter set to on in the HTTP request body. The new item of the day is now item 21. This way, there will be no chance of accidentally selecting the wrong menu item as the item of the day, and you're keeping your API endpoints simple and focused. The next best practice is that you should always provide a way to filter large result sets and rearrange them in ascending or descending order. Using pagination, you can deliver results in smaller chunks. For example, the API /menu items returns all available menu items at once, but a customer may want to see only the desserts or only the main courses. So, your API should be capable of filtering the results. Previously, you've learned that you can accept such filters as query string parameters to retrieve only appetizers or only mains. When building an API, it is always a good idea to enable it to send results in smaller chunks. This way, if the client application wants to display 20 menu items per page, it will not need to make an API call for thousands of items all at once. By using pagination, you can deliver API results in chunks, and clients can decide the page number and how many records they want per page. This API requests 4 items from page number 10 from a total page count of 16. Another good practice is versioning. Did you know that you may break a client's applications if you make changes to your API that might drastically change the response? It's better to be safe and use versioning for your apps. There are several factors to consider when deciding if an updated version is needed or if a modification to an existing representation is enough. In general, you should only support 2 versions of any given resource because maintaining multiple versions can be complex, error-prone, and costly. Next is caching. Previously, you learned that an API should be cacheable because it reduces the load on your database-related API calls. You should always implement caching and send relevant HTTP headers in your response. This will minimize the number of calls your client makes to your API. For example, if the mobile app makes a call to the endpoint menu items, you can cache the result the first time it runs, and then serve the cached result every time after that. This way, you can avoid putting a heavy load on your database every time you need to fetch menu items. You will only update the cache when a menu item is modified or added. For instance, if the appetizers menu is requested, but if there are no modifications to the menu items, all future calls to this endpoint can serve the same cached result without communicating with the database, and that saves a lot of computing power. Last is rate limiting and monitoring. If you want to prevent abuse of your APIs, try rate limiting. This limits the number of times someone can call your API in a period of time, like per minute, hour, or day. Some people even limit their APIs per 30 days. What about monitoring? You should monitor latency to make sure your clients are getting the best possible response time. If you are looking to get the most out of your API, it is essential to also monitor status codes. By keeping an eye on 400 to 499 and 500 to 599 codes, you can assure that your API runs smoothly and identify any potential problems early on. Monitoring network bandwidth is also important to know if someone is abusing your API. It's important to keep your API healthy, performant, and sustainable, and you can do so by following the guidelines and best practices outlined in this video. These included keeping things simple, filtering, ordering and pagination, versioning, as well as caching and rate limiting and monitoring. By keeping to these best practices and standard rules for creating sustainable APIs, you'll be designing great APIs in no time. By now, you should know the best practices for developing APIs, but there is another important aspect of APIs to consider: security. The core purpose of APIs is to make your data more accessible, not just for your apps and websites, but also for third-party clients. This way, your data becomes even more useful. But don't forget, because APIs are publicly available, they may pose a risk to your back-end services. Essentially, APIs give third-party apps access to your server and database. That is why it is crucial to secure APIs. This video covers how to keep your API safe and secure. And you'll learn about various security concepts and how to implement them in your own APIs. First up is SSL, or Secure Socket Layer. SSL encrypts your data and protects your data when it leaves your browser and the web server. When you set up the SSL certificates properly, your APIs can be served over HTTPS. The front-end and mobile application team that works on the Little Lemon project want to ensure that the data is transported securely. So, the API team has used SSL certificates from a reputed provider and installed them. Now all the API endpoints are secured and serve data over HTTPS instead of HTTP. That's why it's important to always check that the endpoint of your APIs starts with HTTPS instead of HTTP. Next is signed URLs. The Little Lemon project team wants to ensure that the API calls are coming to it from their mobile application and their website only. This is where signed URLs come in. Signed URLs give a client application limited access to a specific resource for a brief period of time. With a signed URL, every time an API is called, a particular piece of text called a signature is included with the URL. Server-side code can verify the signature and ensure that the call comes from an authentic source. But how do developers create these signatures? HMAC is a popular signing mechanism used by modern applications. It is easy to use and ensures the authenticity and integrity of the message. For example, some secret message, encoded by a digest algorithm with a secret key, some secret key, creates this HMAC signature. Next, let's discuss authentication. All of us are familiar with usernames and password-based authentication, but sending a username and password to every API call is frustrating, and it's not secure. So, the Little Lemon team prefers using token-based authentication over HTTP-based authentication when securing its API, because basic authentication requires users to send their username and password in every call. With token-based authentication, the user sends their username and password to the sign-in URL and then receives a unique token in text form. After that, every API call will include this token as a HTTP header. The server-side code can check the token, extract the information hidden in it, and match it with an existing user. After this verification, the rest of the work is performed on behalf of that matching user. To create this token, you can use an ad hoc policy from the back-end framework you're using, or you can use something more industry standard like JSON Web Token or JWT. You will learn more about this later in the course. Next, you need to know that there are a couple of popular HTTP codes involved during the authentication process that you should be aware of. 401 means unauthorized. In this context, unauthorized means the username and password don't match, so the server cannot continue further. And then there is 403, which means forbidden. This is an interesting code, and it means that your credentials are valid and you have successfully identified yourself, but you don't have the authority to perform the action. Last is the cross-origin resource sharing or CORS policy and firewalls. When you design an API, you can accept calls from everywhere, or by configuring the CORS headers, you can only accept calls from some specific domains. And finally, another security measure that you can use is firewalls. If you want to ensure that only specific IP addresses can access your API, you can use a firewall application on your server. In this video, you have learned how to protect your APIs. Security is an important consideration when designing APIs, and you are now better positioned to protect your infrastructure and keep your user data safe and secure. The Little Lemon API provides a variety of APIs which allow you to view the details of an order. The output of these APIs may contain sensitive data, such as customers' delivery addresses, which should not be visible to the public. Only manager or delivery crew accounts should be able to access these APIs, and anyone else who tries to access them should be denied. This is where access control comes in handy in an API project. With access control, you can specify which users are allowed to access your API and what data they can see. That way, you can be sure that only the people who are supposed to manage your data can access it. In this video, you will learn about controlling access to your APIs. Roles and privileges are the building blocks of designing an access control system. A role is a collection of privileges, and a privilege is if you are allowed to do a particular task. If you consider the customer role in the restaurant project, it is made of the following privileges. Customers can browse menu items, add menu items to the cart, place orders, add food reviews, and browse their own orders. On the other hand, someone with a manager role will be able to do the following: add menu items, edit menu items, delete menu items, and browse all orders. Managers can also browse customer data, assign orders to the delivery crew, and browse transaction data. And the delivery crew will only be able to perform the following tasks: browse orders that are assigned to them, and update the status of an assigned order. There can be several roles like these in your project. For example, administrators, senior managers, HR accounts, and so on. Each role has a collection of carefully thought-out privileges. The more detailed and specific these privileges are, the better the access control system you can design for your API project. You have probably heard about the term authorization before. It is just another word for access control. Keep in mind that authentication and authorization are two different things. Authentication gets you in, and authorization allows you to do something after authentication or prevents you from doing it. In a real-life project, a user can perform multiple tasks from different roles. For example, the general manager of the Little Lemon restaurant should be able to perform everything an accountant, HR representative, and a normal manager can. So how can you deal with such issues while designing the API? You can create one role and assign all the essential privileges to it. So, a manager will have all the privileges an accountant has. Then you can update or edit these privileges from time to time as needed. This makes it easy to keep your roles up to date and tailored to your needs. The second approach is that one user can have multiple roles. Task-specific roles make it easy to assign the right privileges to the right people. So, your accountants will only have access to accounting features, while your HR team will only have access to HR management features. And there's also a manager-specific role with relevant privileges. This way, you can assign all three roles to the general manager, and they will be able to perform every task an accountant, a HR, and a manager can do. And if you assign a new privilege to the accountant role, the general manager will automatically have that privilege added to their role. API design is not complete without effective access control. By taking the proper time to design and plan out your privileges and roles, you make life easier for developers and avoid costly debugging and refactoring down the road. A well-designed API access control system is an asset for the whole project. It saves time and money in the long run.
Well done. You've successfully kicked off your learning by studying REST APIs. While this information is still fresh in your memory, let's summarize the key takeaways to help embed your newly found knowledge. First, to lay the foundation for the rest of the course, you had a quick summary of what HTTP and HTTPS are. In other words, all the basics. Like how HTTP communication requires a client requesting information, and a server that responds to the request and serves the content. And that HTTPS is better than HTTP because data is encrypted on the client and server side. You also got a refresher about HTTP methods like put, which you use to update a whole resource. And you were reminded of what HTTP requests and responses are, as well as the most commonly used status codes. Following this, you learned about restfulness, naming conventions, and essential tools for API development. First, you learned that REST is an architectural style for designing APIs for a project, and that you can only say that an API is RESTful if specific constraints are met. For example, REST APIs are always stateless. This means that the server cannot identify who is making the request or what their previously requested data was without proper user information. After this, you learned why a consistent naming convention is so important when it comes to APIs. Remember, your endpoints must communicate their purpose, to help you and other developers who might work on your projects. And there are some technical requirements too, like that you should use the / to indicate hierarchical relationships and use nouns for resource names, not verbs. Next, you learned about tools that you can use to develop and test APIs, like Insomnia, which is a powerful free REST API client that has cross-platform versions and a very user-friendly interface. Then, you got a chance for some hands-on learning when you completed an exercise about API development tools and how to set up your tools and environment. And then you moved on to learn more about the principles of API development. This included REST best practices, security, authentication, authorization, and access control. Now those were important. You also discovered that you should only support 2 versions of any resource because maintaining multiple versions can be overly complicated, error-prone, and costly. You also learned that API security is crucial because they give third-party clients access to your databases. And one of the ways you can keep your API secure is to use a signed URL to limit access to a resource for a specific period of time. And you can use token-based authentication, so the client's applications don't have to send their username and password in every call. Next up was access control, which was all about setting roles and privileges for users to make sure only the right people have access to data. You've now covered most of the basic API concepts, and you are ready to complete the quiz and review the additional resources about REST APIs. Well done.
Have you ever tried interacting with a mobile application and got a lengthy loading screen with the content displaying only after some time? You may wonder why an app constantly needs you to wait in some sections while it can display content in others without delay. It might be because most mobile applications now store their information on different servers. To display data from a server, the applications must first make a HTTP call to get it. In Kotlin, a client called Ktor can help make these network requests. In this video, you will explore how HTTP calls are made in Kotlin, learn what Ktor is and how to use it. Imagine you are making an application for the Little Lemon restaurant. At some point, the application needs to request data from the Little Lemon Application Program Interface, or API. When the user opens the menu section of the application, you could use Little Lemon API to get information, such as information about available meals. When users open the menu section, the app requests data from the Little Lemon API, a server that responds to HTTP or HTTPS requests. The Little Lemon API is hosted on an API server that responds to certain HTTP or HTTPS requests. Although the Little Lemon API could support HTTP or HTTPS calls, it is important to always try to use HTTPS instead of HTTP while developing Android applications. Using HTTPS, network requests are encrypted, so your data is secure while being sent to the server. Newer Android versions will completely block HTTP requests. This video will concentrate on the use of HTTPS. On Android, making HTTP requests is done by using networking libraries such as Retrofit or Ktor. These libraries are used by most modern Android applications that need to communicate with servers. Now let's explore how Ktor can be used to make the requests to the API. Ktor is an open-source networking library for Kotlin. The Ktor client is a library for making both synchronous and asynchronous network requests. The Ktor client makes working with type-safe network requests easier. When you want to make a network request using Ktor, you use a Ktor client. The Ktor client is responsible for executing HTTP requests and returning responses. Since Ktor is a multi-platform library, the Ktor client uses an engine to handle the requests. Different engines support different platforms. The engine is the brain responsible for making sure the request executes and the response is returned. To create a Ktor client on Android, you instantiate it with the Android engine. This will assign a working client to the client variable for executing requests. To create a HTTP GET request, you create a line of code that connects to the provided URL, reads the response, and assigns it to the response variable in the form of a HTTP response. If something goes wrong during the execution of the request, an execution is thrown. If the request executes successfully, you can then obtain the response details. Let's examine that part of the process next. Requests executed by the Ktor client result in a response encapsulated in a HTTP response instance. The HTTP response class stores all the server response detail. This includes the request time, the response HTTP status code, for example 200 in case of success, and the body of the response. To obtain the body of a response, you call the body extension function. If the response was returned in JSON format and your client is configured to process JSON responses, the code will convert the JSON response to your custom response body class and assign the instance to response body. Don't worry now if you're not familiar with JSON responses, there will be more on this later in this course. What if you want to make two network calls at the same time? By default, the second call will wait for the first to complete. This way of making two network calls is called a synchronous operation. Multiple calls that execute in parallel will be called an asynchronous operation. For calls to execute in parallel, you need to create code that performs an asynchronous operation. The async block returns a promise to perform the operation in the background and return a result when it is available. This promise comes in the form of a generic deferred instance. To retrieve the promised value, you call await. In this video, you learned how HTTPS calls on Android are managed by using networking libraries such as Ktor. You also learned that you should prioritize the use of HTTPS as they are more secure than HTTP requests. You discovered that a Ktor client is used to execute HTTPS requests and it returns a HTTP response with the result. You learned that the client relies on an engine to execute requests. Lastly, you explored code examples of how to initiate HTTPS calls synchronously and asynchronously and obtain the results.
In this video, you will learn how to make a HTTP call from your Android app using Ktor client. Adrian manages the Little Lemon restaurant. To display the restaurant's menu, he wants the Little Lemon app to make a HTTP call to fetch the data needed from the server. So, let's find out how to get that done. The API call will be made to a URL that leads to a file that contains the menu items to be fetched in the app and displayed on screen. Before continuing, let's quickly observe the existing app code. You can download this from the Course Resources section in a file called Project Code for HTTP Protocol and Asynchronous Calls.zip. It has a header and a download button. There is also an inventory items composable to display the menu items once they have been fetched. Let's also quickly examine the contents of the JSON file that will be returned by the API. You'll find that it contains a menu array with titles for each category. Within Android Studio, you start by creating a menu category class. It has a list of strings named menu. If you examine the JSON file returned by the API, you will see that menu is the name of the field containing the menu item names. Annotate it with @serializable to help the JSON parser automatically parse JSON to it. Now I open main activity. At the top of the class, instantiate the Ktor client. I install content negotiation, calling the JSON function to add support for JSON processing. Then I continue by creating a function named getMenu within the main activity class. I make it private and set it to expect a category string and return a list of menu item name strings. This function will fetch the Little Lemon menu data for a given category. Inside the curly braces, I declare a variable named response of type map with string keys and menu category values. This will hold the response from the get function. Pass the URL for the Little Lemon menu to the get function. To obtain the response as a map of string and menu category, I call the body function. You already know that HTTP calls are asynchronous and that you can use the suspend keyword to mark getMenu as asynchronous. To do this, I add the suspend keyword before the fun keyword that declares getMenu. This ensures getMenu can only be called asynchronously. The response JSON will be now parsed and saved into response. Now you can read the list of menu item names from the menu property of the response map value for the category key and return them, or return empty list if category is not found. And with that, the getMenu function is complete. Now you may ask, when is this method going to be executed? Well, I haven't made that call yet. Let's take care of that next. In the onClick lambda of the button in main activity, I call getMenu with salads and assign its result to a variable named menu items. Remember that getMenu must be called from within a coroutine. Recall that you have a mutable live data field named menu items live data in main activity. Elements assigned to menu items live data are observed by calling observe as state with an initial value of an empty list. It is then used to populate the menu items composable, and so assign menu items to menu items live data.value. Note that this assignment must happen on the main thread. Menu items then takes this data and renders each item from the list by using the single menu item composable. Let's move over to the emulator to examine the output of the code. When you examine the emulator, you'll find that the list of menu items has been successfully rendered. This means the fetch call was successful, and it fetched the data containing the menu items, then displayed it within the app as expected. In this video, you learned how to use the fetch method to make calls over HTTP, and how to handle the response back within your Android app.
You've learned quite a bit about how networking works in Android, but did you know that JavaScript object notation syntax, more commonly known as JSON, can also play a large role in data storage and transfer? You've already become familiar with JSON in a previous course, but let's refresh your knowledge and recap some of the important elements as they relate to data transfer in Android. In this video, you'll be reminded how useful JSON is for processing complex data within mobile apps, particularly when it comes to storing data and communication between client and server during data transfer. JSON is one of the most frequently used data formats for transferring data between a client and a server. It's used in both web applications and mobile applications. In JSON, the data is stored in a JavaScript object format with a key and value pair, or in a JavaScript array of values. JSON is currently the dominant data interchange format for two major reasons. First, it's very lightweight, with its syntax resembling a stringified JavaScript object. Second, it's easier than other methods to handle within JavaScript code, since JSON is valid JavaScript. JSON is language independent and is easy to convert to and from Kotlin objects thanks to the availability of JSON libraries and plugins. In Android apps, you will often use the *2 JSON format to communicate between your client app and the server. JSON is also useful for storing complex states and data. Next, let's revisit the basics of the JSON syntax before exploring its use in storing menu items for the Little Lemon Restaurant app as a JSON object. Recall that JSON names require double quotes, and a colon is used to separate names and values. JSON uses curly braces to enclose objects and uses commas for key-value pair separation within an object. JSON also allows arrays to list out values. Finally, JSON uses square brackets for array declaration and commas for element separation. Let's take, for example, that in the Little Lemon app, you want to store the restaurant's menu items as a JSON object. In that case, the JSON code could contain 3 objects that each represent a menu category: appetizers, salads, and drinks. Each one of them has an array of menu items, and each item is represented with an array index starting from 0. In other words, the first array item under salads, which is Greek, has an index of 0, while the fourth item, which is grilled chicken salad, has an index of 3. To make this data accessible, you'll first need to assign it to a variable. In this case, using the built-in Android JSON library, the value of the val data will be a JSON object instance with the JSON passed in as a string. Now you can access each individual property within the JSON object. For example, let's examine the code you might use to read the fourth item in the drinks array. By typing data.getJSON opening parenthesis, quotes, drinks.getJSON closing parenthesis, quotes, and menu followed by the number 3 in square brackets, you would access the iced tea menu item. Some JSON libraries such as JSON and Moshi make accessing JSON data even easier. This representation and structure are why JSON is so popular. It is easy for both humans and computers to process and understand. If you work with retrieving data from APIs, converting the JSON strings to Kotlin objects will be a standard workflow. You can then easily access the object's properties programmatically. This is a vital developer skill that you should practice. In this video, you revised your previous learning about JSON. You learned how JSON is useful in processing complex data within mobile apps. You should now appreciate how to use it in your native Android apps to store data and communicate between client and server while transferring data. In a previous video, you revisited JSON. You learned about JSON and how it relates to Kotlin objects. In this video, you will observe JSON in practice. To convert JSON strings to Kotlin objects and back, you will use the JSON library. JSON is one of the most popular libraries for working with JSON in Kotlin and Java. Little Lemon has a JSON representing table reservations. In Kotlin, a multi-line string can be expressed by triple quotes. The reservations JSON variable holds all the reservation information in a JSON string format. JSON strings are easy to receive and send over the network. It is easier to work with the data if it is stored as Kotlin data classes. I will define a reservation class with two fields, table4int and string time, to store the reservation data. I will define the allReservations class with two fields, string date and list of the reservation. With the help of the JSON library, you can convert JSON strings to a Kotlin data class. First, you add a JSON dependency to your project by updating Gradle dependencies. I will open the build.gradle file located in the app module. I will add a JSON dependency and sync the project. To parse the JSON string into JSON, I will first create an instance of a JSON object in the main activity.kt file. With the JSON instance, you can obtain Kotlin objects from the JSON string by calling the fromJSON method. I will pass in the reservations JSON string together with the allReservations class. I will iterate over the allReservations object and print the details of each reservation. I run the code and review the output. I will open logcat panel. In the logcat panel, I can see reservation time and table information for each restaurant. I will close logcat panel. Now consider the scenario where you have a Kotlin object and you want to send that content through the network. Well, one straightforward way would be to first convert to a JSON string. To do that, you can use the same JSON instance you instantiated earlier. This time, however, you call toJSON and pass all reservations. In this video, you practice converting a JSON string to a Kotlin object and the other way around. Working with JSON will be an everyday task in your career as an Android developer. Well done! You've reached the end of this week, and it was all about interacting with REST APIs in Android. Let's take a few moments to review what you have learned. You explored how HTTP calls are made in Kotlin, found out about Ktor and how to use it. You discovered that making HTTPS requests is done by using networking libraries such as Ktor. The app will request data from an API server that responds to HTTPS requests. The Ktor client is instantiated with the Android engine. This assigns a working client to the client variable for executing requests. The engine is the brain responsible for making sure the request executes and the response is returned. The response can get returned in a JSON format and then is converted by a custom response body class and assigned to response body. A synchronous operation is a way of making two network calls, but just one call at a time. Multiple calls executing in parallel are called an asynchronous operation. To practice some of those concepts in action, you explored code examples of how to initiate synchronous and asynchronous HTTPS calls, and practice requests and responses in Kotlin. Since JSON is involved in many of your network operations, you revised your current JSON knowledge and learned how JSON can be used to process complex data within mobile apps. This included observing how the JSON data is stored in a JavaScript object format with a key and value pair, or in a JavaScript array of values. You use the JSON format to communicate between your client app and the server and for storing complex states and data. You revisited some basics of the JSON syntax, such as names and arrays. You worked with examples to retrieve data from APIs and convert the JSON strings to Kotlin objects. In addition, you interacted with Android REST APIs to fetch images URLs and to parse data in Kotlin. That's the end of your study for this week, where you covered many practical areas of interacting with REST APIs in Android, such as sending and receiving HTTPS calls and working with data formats. Well done.
We all use data and databases in our daily online lives. For example, uploading photos to our social media feeds, downloading files at work, and playing games online are all examples of database usage. But what exactly is data, and how does it interact with a database? If you're struggling to answer these questions, don't worry. By the end of this video, you'll be able to describe what a database is at a conceptual level, identify real-world examples of the use of databases, and demonstrate an understanding of how data is organized in a database. So, let's return to the first of our questions. What is data? In basic terms, data is facts and figures about, well, anything. For example, if data were collected on a person, then that data might include their name, age, email, and date of birth. Or the data could be facts and figures related to an online purchase. This could be the order number, description, order quantity and date, and even the customer's email. Data is crucial for individuals as well as organizations. But where is all this data stored? In our digital world, data is no longer stored in manual files. Instead, developers use something called databases. A database is a form of electronic storage in which data is organized systematically. It stores and manipulates data electronically to make it more manageable, efficient, and secure. There are many real-world examples of where databases are used. For example, a bank can use a database to store data for its customers, bank accounts, and transactions. And a hospital uses a database to store patient data, staff data, laboratory data, and much more. At this point, you might be asking yourself, but what does a database actually look like? Well, a database looks like data organized systematically, and this organization typically looks like a spreadsheet or a table. What exactly does the term systematic mean? All data contains elements or features and attributes by which they can be identified. For example, a person can be identified by attributes like their age, height, or hair color, and this data is separated and stored in what's known as entities that represent those elements. As you just learned, an entity is like a table. It contains rows and columns that store data relating to a specific element. In other words, these are relational elements. They're related to one another. These entities could be physical representations, like an employee, a customer, or a product, or they could be conceptual, like an order, an invoice, or quotation. Entities then store data in a table-like format against the attributes or features related to the element. For example, an online store could hold customers' data in a customer entity containing specific attributes relating to the customer. These attributes could include first name, last name, date of birth, and email. And they could also have product data stored in a product entity against attributes like product code, description, price, and availability. In the relational database world, these entities are known as relations or tables. The attributes become the columns of the table, and each table row represents an instance of that entity. As an example, let's take the entities from the online store example that you just explored. These two examples could be combined into a list of orders the store received from its customers. Within a database, this data could be rendered as an order table or entity, and the data could be organized into rows that contain a unique order number, the name of the customer who placed the order, the product that they ordered, and the price of that product. There are many ways to organize data in a database. Relational databases aren't the only kind of databases that you'll encounter. As a database engineer, you'll work with many different types of databases. Here's a few common examples of other types of databases. An object-oriented database is where data is stored in the form of objects instead of tables or relations. An example of this kind of database could be an online bookstore. The store's database could render authors, customers, books, and publishers as classes, like sets or categories. The objects, or instances of these classes, would then hold the actual data. Graph databases store data in the form of nodes. In this case, entities like customers, orders, and products are represented as nodes. The relationships between them are represented as edges. And finally, there's document databases where data is stored as JSON, or JavaScript Object Notation objects. The data is organized into collections like tables. Within each collection are documents written in JSON that record data. So in this example, customer documents are held in a customer collection, while order and product documents are stored in the order and product collections. But where are the databases themselves stored? A database can be hosted on a dedicated machine within the premises of an organization, or it could be hosted on the cloud. Cloud databases are currently a more popular choice. This is because they allow you to store, manage, and retrieve data through a cloud platform and access data through the internet. And they all provide a lower cost option for data management than other similar options. You should now understand the concept of a database. You should also be able to identify examples of databases and demonstrate how data is organized within a database. Great start. You'll be storing and managing data in no time. Picture yourself in the following scenario. You're managing the database of a large online store. Your database must be able to retrieve a customer's details from one table and then find the order recorded against another table. So how does the database establish a relationship between these pieces of data? Over the next few minutes, you'll explore this process, and by the end of this video, you'll be able to explain why data in a database should be related and identify an instance of related data in a database. Data stored in a database cannot exist in isolation. It must have a relationship with other data so that it can be processed into meaningful information. So how do you make sure that all the data in your database is related? Let's explore how data is related by using the online store as our example. In the database of your online store, you could have an order table and a customer table. To locate the details of a customer's order, you would check the order number against the customer ID. In other words, the database establishes a link between the data and the tables. Let's look at the customer table in more detail. In this table, the columns are customer ID, first name, last name, and email. In relational database terms, these are fields. Then there are several rows which contain data for each of these fields. In relational databases, they are known as records of the table. So, all these fields and rows work together to store information on the customer, also known as the entity. Every row and record in the customer table is an instance of the customer entity. For example, Sarah Hogan, who has a customer ID of C1, is one customer instance. And Katrina Langley, who has a customer ID of C4, is another customer instance. What's most important is that each of these customer instances, or records, must be uniquely identifiable. But what if two or more customers share similar info, like the same first name or last name? To avoid this confusion within the database, you can use a field that contains only unique values like the customer ID. This is called a primary key field. It contains unique values that cannot be replicated elsewhere in the table. So even if two customers share the same name, they'll still have separate customer IDs. This means that your database can determine which customer is the required one. Let's look at the order table next. Just like the customer table, the order table also has fields and records. And in this table, the primary key field is the order ID. But there's also a field named customer ID with the exact same data as the customer data. So what is the purpose of the customer ID in this table? The customer ID is there to help identify who it is that placed the order. So by adding the customer ID field to the order table, a relationship is established between the customer table and the order table. And because of this relationship, you can pull data in a meaningful way from both tables. The customer ID field in the order table is known as the foreign key field. A foreign key is a field in one table that connects to the primary key field in the original table, which in this case is the customer table. So the customer ID is the primary key of the customer table, but it becomes the foreign key in the order table. This way, the relationship is established and the data in these two tables are related. You should now be able to explain the relationships between data in a database and identify instances of related data. Great work. At this stage in the course, you're probably familiar with the basics of databases and how they store and manage data. But it's also important that you know how to interact with databases in order to work with data. As a data engineer, you can interact with databases using structured query language, or as it's more commonly known, SQL, also pronounced as SQL. Over the next few minutes, you'll learn how to explain what SQL is and outline the role of SQL in databases. So what sort of interactions do database engineers need to establish with databases? Some of the operations you could carry out in the data might require you to create, read, update, and delete data. These operations are also known as CRUD operations. You might already be familiar with some of these operations. If not, don't worry. They'll be covered in depth at later stages in this course. Let's find out more about SQL. SQL is a standard language that can be used with all databases. It's particularly useful when working with relational databases, which require a language that can interact with structured data. Some examples of relational databases that SQL can interact with include MySQL, PostgreSQL, Oracle, and Microsoft SQL Server. The next question this raises is, how does a database interpret or read and execute instructions given using SQL? A database interprets and makes sense of SQL instructions with the use of a database management system, or DBMS. As a web developer, you'll execute all SQL instructions on a database using a DBMS. The DBMS takes responsibility for transforming SQL instructions into a form that's understood by the underlying database. This was just a very quick introduction to SQL. At this early stage, you should be able to explain what SQL is and explain the role of SQL in databases. In the upcoming videos, you'll learn more about SQL and develop a deeper understanding of the language. Imagine that you've just been hired to create a database for a college. First, you'd need to create tables to hold data in all aspects of the college. Then you'd need to insert data into these tables, and then modify this data whenever something changes. That's a lot of work, but it's all possible with the use of SQL and CRUD operations. Not familiar with these operations? No problem. Over the next few minutes, you'll learn how to explain the tasks that SQL syntax is used for when building a database, and demonstrate an understanding of the SQL subsets and sublanguages. So, let's return to our college database scenario. How can you possibly make all these changes in the database? Well, with the help of what web developers call CRUD operations. Performing CRUD operations is the most common task when working with a database. CRUD stands for create, read, update, and delete. Or in operational terms, create, add or insert data, read data, update existing data, and delete data. Alongside these operations, there are many other things that SQL can do. Depending on what SQL is used for, it can be divided into many subsections or sublanguages. These include DDL, or Data Definition Language, DML, also known as Data Manipulation Language, DQL, or Data Query Language, and DCL, also called Data Control Language. Let's take a closer look at these languages and their commands, starting with Data Definition Language, or DDL. DDL, as the name says, helps you define data in your database. But what does it mean to define data? Before you can store data in the database, you need to create the database and related objects like tables in which your data will be stored. For this, the DDL part of SQL has a command named create. Then you might need to modify already created database objects. For example, you might need to modify the structure of a table by adding a new column. You can perform this task with the DDL alter command. You can remove an object like a table from a database using the DDL drop command. Data manipulation language, or DML commands, are used to manipulate data in the database, like inserting, updating, or deleting data. Most CRUD operations fall under DML. To add data to a table, you can use the insert command. This command lets you specify the fields to add data to, along with the values to be inserted. If you need to edit data that's already inserted into a table, just deploy the update command. And you can specify data to be removed by using the delete command. So far, you've learned how to add database objects and manage data within them. So how do you read or retrieve that data? To read data stored in a database, you can use data query language. DQL defines the select command to be able to retrieve data. Select lets you retrieve data from one or multiple tables, letting you specify the data fields that you want based on preferred filter criteria. And finally, you can also use DCL, or data control language, to control access to the database. For example, using DCL commands, you control access to data stored in the database. Grant and revoke DDL commands are used to give users access privileges to data and to revert access privileges already given to users. You should now be familiar with how SQL acts as the interface between the database and its users. And you should also be able to identify SQL operations in sublanguages. Great work. As you might already know, you can interact with the database using SQL. But just like with other coding languages, you need experience with SQL syntax and its subsets before you can make use of it. Over the next few minutes, you'll learn how to create a database using the data definition language, or DDL subset of SQL, utilize the data manipulation language, also known as the DML subset, to populate and modify data in a database, and read and query data within databases using the data query language, or DQL subset of SQL. In order to demonstrate SQL syntax and its subsets, I'm going to show you the SQL commands that can be used to develop a database for a college. However, take note that the demonstration which follows will only briefly show each step in the process. You just need to develop a working familiarity with SQL for now. You'll explore the language and its subsets in much more detail later in this program. The first task is to create the database. To do this, I write a create statement using SQL's DDL subset. So, the syntax to create a database is create database, followed by the name of the database. I then place a semicolon at the end of the statement. Let's create a college database as an example using the syntax create database college. Once you've created a database, the next step is to create the tables. You can create tables using the create table syntax, followed by the table name. Just repeat these same steps for each new table you want to add to your database. I can use this syntax to create a student table in my college database. This table will hold information on each student. To create the table, I just write create table student. Now I need to populate the table with data. This is where I can use the data manipulation language, or DML subset of SQL. To add table data, I use the insert into syntax. This inserts rows of data into a given table. I just type insert into, followed by the table name, and then a list of required columns or fields within a pair of parentheses. Then I add the values keyword and specify in order the values for each of the fields. As an example, let's add data to the student table in our college database. I'll use the student table I created earlier and add student data to it by specifying values for each of the following columns: ID, first name, last name, and date of birth, and then populate the table with the required data. But what if I need to update or modify data? For example, let's say I've input the wrong date of birth for a student. To change this data, I can use the update syntax, which is part of the DML subset of SQL. First, I add the update keyword, followed by the student table name. Then I use the set keyword, followed by columns and values I want to update, written as key value pairings. In this instance, it's the date of birth column and a new date of birth value. Finally, I add the where clause and a condition to filter the records I need. For example, To change the data for the student with the ID of 2, I can type where ID equal to 2. It's also possible to delete data from a table. Let's delete the table record for the student with the ID of 3 using the delete syntax. First, I type delete from, then the table name. This tells MySQL where the data must be deleted from. This is followed by the where clause and a condition such as ID equal to 3, which would remove all data on row 3 of the table. So I could instruct MySQL to remove the data of the student on row 3. Once I run the statement, the student's data is removed from my table. You're now familiar with how to add, update, or delete data in a database. But how would you read data stored in your database tables? That's where SQL's DQL, or data query language, comes in. The main syntax of DQL is select. As its name says, it's used to select data from the database. A select statement is written using the select keyword, followed by the columns that hold the data you required. You then write the from keyword, followed by the name of the table you want to select data from. As an example, you could use the select statement to query the student table to find the name of the student with an ID of 1. You would just need to add the where keyword, followed by the student's ID. This would then return the name of John Murphy. You're now familiar with the basics of SQL syntax and its subsets. Don't worry if you're still trying to figure out these subsets. You'll explore each of them in more depth later in this specialization, and you'll also get an opportunity to try them for yourself. You've just been hired by an online bookstore to build and maintain databases that can store information on millions of books and customers. But how do you even begin to create and alter databases that store constantly expanding information or process millions of orders from all over the world? The answer to these questions lies in SQL create and read commands. In this video, you'll learn how to create a database using SQL syntax, and you'll also discover how to drop or delete a database. However, before you create a database, you first need a clear idea of its purpose. For example, if you're building a database for an online bookshop, then your database needs to record data like book titles, authors, customers, and sales. The data on these topics must be stored and organized in relevant tables in a database. Users can then access, retrieve, and update the data as needed. So how can you create a database using SQL syntax? To create a database, just type the create and database keywords. These keywords are then followed by the name of your database. But what about removing or dropping a database? To drop a database, just type the keywords drop and database. Then follow these keywords with the name of the database you want to remove. Let's look at these keywords in action. To create a database, I need to use SQL syntax. To demonstrate, let's create a second bookstore database using SQL syntax. First, I type the keywords create and database, followed by the name of my new database. In this case, the database is called bookstore2_db. I always use a meaningful and relevant name when creating a new database. This helps to make it easier to document my work. Database names must also be unique and can only have a maximum of 63 characters. If my database name doesn't meet these requirements, then an error message will appear. Finally, I add a semicolon to the end of the statement. Then I run the statement, and the new database bookstore_db2 appears in the left-hand sidebar. So, I've created a second database. I can also remove databases using SQL statements. First, I select the SQL tab. Then I input my query in the code box that appears. I type the keywords drop and database followed by the name of the database I want to delete. In this case, it's bookstore_db. Now I run the query. Then SQL deletes the database. In this video, you learned how to create and delete databases using SQL syntax. Great work. At this stage of the course, you're probably familiar with the basics of how databases store and interact with data. But how do they store all this data and present it in a logical way? In the form of tables. By the end of this video, you'll be able to outline what a database table is at a conceptual level and explain how data is structured in a database table. As you probably already know, the table is made up of rows and columns which hold data, and a table is stored in a database. In a database that holds multiple tables, these tables are known as relations, as they all relate to one another. In a more conceptual or logical sense, a table is also known as an entity. And in object-oriented databases, or OODB, an entity is an object that has attributes that are like columns or fields in a table. So in essence, a table, entity, and object all refer to the same concept. Within every table are columns, also sometimes called fields or attributes. Each column or field has a unique name and data type. For example, I have a table that contains data on employees in a company. The table organizes the data into columns such as ID and role, and each column can hold different types of data like numeric or string. A set of columns or fields form a row. In relational database terminology, a row is known as a record. So a record is a combination of columns or fields that contain data. In my employee table, for example, each row is a single employee record. Let's return to columns for a moment. As you now know, every column has a data type. The data type of a column defines what type of value a column can hold, like integer, character, date and time, and so on. It's up to the developer to decide the data type for each column. And it's also a guideline for SQL around what data type to expect in each column and how to interact with the underlying data stored physically. However, data types can vary depending on the database system. For example, you might have different types for MySQL, SQL Server, or Access. Always refer to the documentation of the relevant database system to check what data types it supports. Generally, all database systems support string data types for storing characters in strings of characters, numeric data types to store exact or whole numbers and approximate numbers, date and time data types to store information on date and time, and binary data types to store images, files, and other information. Another important concept related to tables is domains. A domain is the set of legal values that can be assigned to an attribute. Basically, this means making sure that the values a field can hold are well defined. For example, you can only place numbers in a numerical domain, and you can only place characters or strings of characters in a string domain. And each of these domains must include length, values, and other relevant rules that define its function. Each row or record in a table is also uniquely identified by what's known as a primary key. A column in the table that has unique values will become the primary key of the table. In the employee table, for example, the ID column is the primary key as each ID is unique. This is because the other columns could contain repeating values. For example, two employees may share the same name or role. It's also possible for a primary key to be a combination of columns if a single column alone doesn't possess unique values. You should now be familiar with what a database is and be able to explain how it is structured. You should also be able to explain key concepts such as columns, rows, and keys. Great work. You probably know that database tables store data in the forms of columns and rows. But how do you make sure that every column accepts the correct type of data? For instance, that your cost column stores values in decimal, or your product quantity column accepts positive numbers. This is exactly what data types do. With data types, you can determine what kind of data is accepted by each field in your table. Over the next few minutes, you'll learn how to explain the numeric data type in a database and differentiate between integer and decimal data types. Before you begin exploring numeric data types, let's take a moment to explore the concept of data types. When you create a table in a database, you need to define column names and the data type of the content that will reside in those columns. Data type tells a database management system, such as MySQL, how to interpret the value of the column. Data types maintain data in the right format and make sure the value of each column is as expected. The most used data types are numeric, string, and date and time data types. Let's take the example of a table from the database of an online store. This table collects information on customers in the form of columns called customer name, order date, product quantity, and total price. Each of these columns must store data in the form of a suitable data type. The customer name column can use string data, order date can use a date type, and product quantity and total price columns are best suited to numeric data. The focus of this video is the numeric data type. Numeric data types is the generic term used for all specific data types that let a column store data as numbers in the database. The two most common numeric data types used in databases are the integer data type, used for a whole number value, and the decimal data type, used for a number with a fraction value. To return to our earlier table example, the product quantity column is defined as an integer data type. This is because it holds whole numbers only. Fractional numbers can be inserted, but they'll always be automatically rounded up or down to the nearest whole number in the database. And the total price column is a decimal type. This is because it holds fractional numbers. For example, an item that costs $80.90 is a fractional value. 80 is a whole number and 90 is a decimal. Whole numbers can also be inserted. The database will add a decimal point along with a fractional value of 0. In most database management systems, you'll find different types of integer and decimal data types. Each type is intended to store a minimum and a maximum number value. For example, in my SQL database management system, tinyInteger, or tinyInt, is used for a very small integer number value where the maximal possible value that can be inserted is 255. While integer or int can be used to store a very big number, the maximum value that it can store is over 4 billion. These data types can also accept negative and positive values. In some database management systems, you can also force columns to accept positive numbers. This increases the maximum value they can store. You should now be able to explain the numeric data type in a database, and you should also be capable of differentiating between integer and decimal data types. Great work. You probably already know that when you create a table in a database, you must define the column names and the data type of the content that will reside in those columns. You can use a string data type to define a column's data type, particularly in instances when it accepts both numeric and text characters. In this video, you'll explore the string data type, and by the end of the video, you'll be able to explain the string data type in a database and differentiate between char and varchar data types. When you create a table in a database, it is important for data integrity to ensure that only valid values are inserted in your table. For example, you should use string data type when you intend to store data that contains a mix of character types. So if you define a column as a string, then any type of text can be inserted. This includes alphabet characters, numeric characters, and special characters. Let's explore an example to find out more about how string data types work. Let's take the example of a student table from a college database. This table stores student login information for the college's online portal. It stores this information under the following 4 columns: student name, username, password, and email address. The student name column contains only alphabet characters. The username column contains alphanumeric characters, and the password and email column contains a mix of character types. String data type is a generic term used for different string data types in the database. The most used string data types are char, which stands for character. This data type is used to hold characters of a fixed length, and varchar stands for variable character. This holds characters of a variable length. Let's explore these string data types further. Char means that the given length of the characters is predetermined. It can't be changed after declaration. Column attributes are defined as char followed by a character length in parentheses. For example, char 50 means that a column only permits 50 characters of space in each field. Char is the best option if you have a predefined size of character that you want to maintain. In the student table, you can set a maximum length of 50 characters for the username column in SQL with char 50. For example, the table contains the records for a student with the username Mark123, which is a total of 7 characters. However, because the column is defined as char 50, this username occupies a length of 50 characters within a space. The varchar data type works in a similar way to char. However, it is a variable length. This means that the length can be changed, it's not fixed. Varchar is often used when you're not sure how many characters might be inserted in a column field. So you can type varchar 50 in SQL to allow for any input up to a maximum of 50 characters. In the student table example, the student name column would most likely contain names of varying length. So you could define the student name column as varchar 50 in SQL. This means that the name of each student only occupies as much space as there are characters in their name. For example, Mark Simpson occupies far less than 50 characters, but this field could hold a name up to the value of 50 characters if required. Finally, let's briefly explore some more commonly used examples of string data types. Tiny text is used to define columns that require less than 255 characters, like short paragraphs. Text is used to define columns of less than 65,000 characters, like an article. Medium text defines columns of 16.7 million characters, for example, the text of a book. And the long text data type stores up to 4 gigabytes of text data. You should now be able to explain the string data type as used in a database, and you should also be capable of differentiating between string data types, including char and varchar. Great work. To ensure the accuracy and reliability of the data in your database, you must limit the type of data that can go into your database table. In this video, you'll learn how to describe the purpose of constraints in a database and identify default constraints to set default values in a table. Database constraints are used to limit the type of data that can be stored in a table. This ensures that all data inserted into the table is accurate and reliable. If the database detects a violation between the constraint and the data operations, then it aborts these operations. An example of a violation might be an attempt to insert or upload invalid data to a table. The database realizes that the data is invalid and rejects it. Constraints can be column level, where the rule applies to a specific column. They can also be applied at table level. For example, I could use the foreign key constraint to prevent actions that would destroy links between tables. I'll demonstrate this in more detail in a later lesson. Two of the most used database constraints include not null, a method of preventing empty value fields, and default, a method of assigning default values. For now, let's begin our exploration of default values with the not null constraint. The not null SQL constraint is used to ensure that data fields are always completed and never left blank. Let's explore this concept using the example of a table from an online store that records the IDs and names of customers. The table records this data in its customer ID and customer name columns. These columns must always contain data. If there's no data or values inserted into either of these columns, then the creation of a new customer record is aborted. The not null default value is implemented using a SQL statement. A typical not null SQL statement begins with the creation of a basic table in the database. I can write a create table clause followed by customer to define the table name, followed by a pair of parentheses. Within the parentheses, I add 2 columns, customer ID and customer name. I also define each column with relevant data types. Int for customer ID as it stores numeric values, and varchar for customer name as it stores string values. Finally, I also declare a not null constraint for each column. This makes sure that neither column will accept null values. Now, any operation that attempts to place a null value in these columns will fail, like inserting or updating data. Next, let's look at how the default constraint works in a table. The default constraint sets a default value for a column if no value is specified. This means that if no data is entered for a specific field within a column, then the table will automatically insert a default value instead. To gain a better understanding of default values, let's look at a table that holds player records for a football club's database. The table is called Player Table and contains 2 columns. The first is player name and lists the names of each player in the team. And the second column is city and lists which city each player is from. Most of the players in this club are from Barcelona, so I can specify a default value of the city column as Barcelona. This means that I don't have to enter Barcelona repeatedly into the city field for each new player. If no value is entered in the table, then each field is automatically filled with the default value of Barcelona. Let's find out how the default command is incorporated into a SQL statement. First, I use the create table commands to create a table, and then call it player. Then within a pair of parentheses, I input the column names, assign a string data type for each, and assign a default value of not null for the name column. Finally, I add the default keyword statement, followed by the default value Barcelona for the city column. Now when I add data into the table for a new player, I don't need to type in Barcelona for players who are from the city. Instead, it will be inserted automatically. You should now be familiar with the importance of using database constraints. You should also be able to explain database constraints as a method of enforcing rules on a column or table level. Good work. Building a database involves working with substantial amounts of data. But how do you organize your data so that you can find exactly what you need and make sense of it? With SQL, you can create a table within your database to hold and organize your data. In this video, you'll learn how to create tables in a database management system using SQL syntax. Let's begin with a look at the SQL create table statement syntax. I begin the statement with the keywords create table to let SQL know that I want to create a new table. I then add the name of the table I want to create. Finally, I add a pair of parentheses. Within these parentheses, I type the name of each column that must be included within the table, followed by its respective data type. Now that you're familiar with the syntax, let's look at it in action. Be aware that before you can create tables, you must already have a database on the server. In other words, you can't build tables if there's no database to create them in. So let's assume that I already have a database ready to work with. In this example, I'll create a customer table in the bookstore database to store customer data, like names and phone numbers. First, I write a SQL statement that contains the create table commands followed by the name of the table, in this case customers. Then I add an open parenthesis. It's within this parenthesis that I need to create my own columns. So, I write the name of my first column, which is customer name. This is followed by the data type varchar. This data type means that the column can hold data of any type. I then add a numeric value within a pair of parentheses. Then I add a comma and write the name of the second column, which is phone number. I add int as the data type so that only whole numbers can be stored. Then I add a closing parenthesis and a semicolon. Finally, I execute the statement. The customers table is now stored in the database. In this video, you learned how to create tables in a database using SQL syntax. Well done. At this stage, you're probably familiar with creating tables in databases, but no table is ever static. Database developers are always restructuring tables. Sometimes they need to add new columns, delete old ones, or edit the data they contain. You can complete many of these basic restructuring actions using SQL syntax. In this video, you'll learn how to alter a database table by adding and removing columns, and modify the attributes of a database table. Let's start by exploring the SQL alter statement syntax. The first part of an alter statement is the alter and table keywords. These keywords inform the database that there is a table whose contents must be altered. This is followed by the name of the table to be altered. I then include the add keyword. This keyword tells SQL that there's one or more items to be added to the table. There are other keywords I could include here instead, but for the purposes of this example, I'll work with add. Finally, I insert a pair of parentheses. Within these parentheses, I declare the name of a new column to be added to the table, along with this data type. Now that you're familiar with the alter table statement, let's explore an example of this statement in action. However, before you can begin altering tables, you must already have a database on the server. So, as always, make sure that you know how to create databases before proceeding, and ensure that you already have a table in your database with data that you can alter. In my example, I have a students table located within the database called college. My students table holds information on the IDs, names, and emails of each student in a college. I can demonstrate the alter statement by adding, deleting, and modifying columns in this table. My first task is to add 3 new columns to the table: age, nationality, and country. To add these columns using SQL syntax, I first type the alter table command, followed by the name of the table, students. Next, I use the add command to let the database know that I want to add new columns to the table. Then I input a pair of parentheses that contain the columns I want to add, along with the type of data they'll hold. These columns are an age column, which holds data in integer format, a country column with varchar as the data type, and nationality and country columns that hold varchar or string data. I also add a character limit of 50 to the country columns fields and a limit of 255 to the nationality columns fields. Then I execute this statement. I now have 2 new columns in students table in the college database. Country and nationality are very similar columns, and in most cases will probably hold the same type of information. So I can write a SQL statement to remove the nationality column. Just like the last example, I start my statement with alter table students table. Next, I type the drop column command followed by nationality. This command instructs SQL to delete or drop this column from the table. Then I run the statement. A notification message appears requesting confirmation of deletion. I press OK to confirm. The nationality column has now been dropped. Now it's time to alter the structure of the table. The country column has a limit of 50 characters, just as I said it originally. But now I'm going to change it so that it holds 100 characters instead, using the alter table command. I start with the syntax alter table, followed by students table. Then I type the modify command, the country column name, and the varchar data type. And finally, I add a pair of parentheses containing my new value of 100. I then execute the query. My country columns limit has now been updated to 100 characters. In this video, you learned how to alter and modify tables in a database using SQL syntax. Well done. When working with databases, you'll often have to add new rows and columns to existing tables or even create new tables from scratch. For example, if you run a college database, you'll have to add new rows for every new student. With SQL, you can perform these tasks quickly using the insert statement. By the end of this video, you'll be able to identify and understand insert SQL syntax and insert data into tables with the use of the insert into clause. Let's begin with an exploration of the insert into syntax. To write an insert statement, first write an insert into clause. Then specify the table name followed by a list of columns contained within a pair of parentheses and separated by commas. Then use the values keyword and write a list of values within a pair of parentheses. It's important to remember that each value corresponds to a specific column and so should reflect the same data type and order. You can also add multiple rows into a table at the same time. First, write the insert into clause in table, just like before. Then use the values keyword and add multiple rows of values. Just make sure that each new row is separated from a previous one by a comma. Now let's explore some examples of an insert statement. In this example, I'll use a table called players from a sports club database, and I want to insert new player data into this table. First, I write the insert into command, followed by the name of the table. In this case, it's players. Then I add the column names within a pair of parentheses. These columns must contain the basic information that the club requires about each player. So I'll name the columns ID, name, age, and start date. Next, I insert the values keyword and then add the values I want to assign to each column within a pair of parentheses. I start adding the data for a new player named Yuval, age 25, with an ID of 1 and a start date of 2020-10-15. It's important to use the correct format of year, month, and day when entering dates in a table. Otherwise, an error message will appear. I can also use the current date function followed by a pair of empty parentheses next to my values, just like I've done for the new player Yuval. Now that I've scripted all values for Yuval, note that each value relates to a specific column. Number 1 corresponds to the player ID column, Yuval to player name, 25 to player age, and the date to start date. This means that the order in which I type my values within the parentheses is very important. Otherwise, I might accidentally store these values in the wrong columns. It's also important to note that all non-numeric values are placed within quotation marks, just like Yuval and the date value in this statement. Finally, I execute the statement. The output now shows one row of data for Yuval, just as my code instructed. But what if I wanted to insert multiple records of data into the table? Let's say that 2 new players have joined the team. The first player is Mark, age 27, with an ID of 2 and a start date of 2020-10-12. And the second player is Carl, age 26, with an ID of 3 and a start date of 2020-10-7. Both Mark and Carl must be inserted into the database. As you learned earlier, this is a very straightforward task. First, I write the insert into command. Then I write the table name, players. Next, I type the ID, name, age, and start date columns within a pair of parentheses. Then I write the values keyword and insert 2 records of data. These data records are contained within 2 pairs of parentheses separated by a comma, one for Mark and another for Carl. Finally, I run or execute the statement. I then check my output, which shows that all 3 players are now in the table. So far, I've explored how to add data to the table. but it's also possible to show existing data in the player table by executing the following SQL query. First, I type the select clause, followed by an asterisk. This asterisk tells SQL to return all columns within the table. Then I type the from keyword and the name of the table. I execute the statement, and the output shows all data available from the player table. You can now identify and make sense of the insert syntax, as well as insert new data into tables with the insert into clause. Good work. There will often be times that you'll need to query data from a table in your database. For example, you might need to retrieve a list of names from a table, or return a set of results from a math calculation. You can perform these actions using the select statement, and that's what I'll demonstrate now. So over the next few minutes, you'll learn how to utilize the SQL select statement to query data from a table in a database, and perform other SQL select tasks, such as math calculations, date and time queries, and concatenation functions. To get started, let's explore the syntax of a SQL statement. A basic SQL select statement is written as the select keyword, the name of the column that contains the data you need to query, then the from keyword, and finally the name of the table you want to query. For example, if I want to query data about the names of players from a soccer club database, I could use the following syntax: the select keyword, the player name column, and the from keyword, and finally the name of the table, which is player table. And although it's not mandatory, a semicolon is often added to mark the end of a SQL statement. Let's take a closer look at how this statement works. As an example, I'll extract information from a table called players held in a soccer club database. This table records details about players in a soccer club like ID, name, age, and skill level. I can use the SQL select statement on this table to obtain information on the club's players. The expected outcome of this select query is that it will return a result set that displays all player names held in the table. I can write the statement as select name from players. The select command is used to retrieve data. Name is the column that stores the player's name in the database. From is a keyword that identifies the source table, and players is the table name. I then run the statement. The query returns a table column that lists the players' names from the players' table, with each name on its own row. So in the example you just explored, I retrieved data from one column in a table. But what if I wanted to retrieve data from multiple columns? Maybe I need to retrieve the name and skill level of each player. I can obtain this information using a SQL select statement written as select name level from players. I add a comma between name and level so that SQL understands they are two separate columns. I run the query and it returns the data from the name and level columns in the players table. I could also use the select statement to retrieve all data from all columns in the players table. There are two methods I could use to achieve this. The first method is to list all column names in a standard select statement as follows: select ID, name, age, level, from players. Once again, each column is separated by a comma. I then run the query and get all the requested information in table format. The second method is to use an asterisk as shorthand. So instead of typing out all column names, I just type select asterisk from players. Then I run the query. It returns all the information available in all table columns, just like in the first method. You're now familiar with how to use the select statement in MySQL. So, next time you need to query data in your database, you've now got different methods to choose from.
I recently created a database table for a college called Student Table. It contains the following pieces of data on each student in the college: ID, first name, last name, home address, college address, contact number, and department. Let's use the update syntax to update the home address and contact number of the student assigned the ID of 3 in the table. So I click the SQL tab in PHP-MyAdmin. Now I use the update clause followed by the name of the table that I want to update, which is student table. Then I add the set clause followed by the names of the columns to be updated, which are home address and contact number. Next to the name of each column, I add an equal to symbol and place the new values to be inserted into the table in single quotation marks. I also make sure to separate these column value pairings with a comma. Finally, I add the where clause to identify the exact record I want to update. This record has a student ID column field that was assigned the value of 3. So I write where ID equals 3. Now that I've completed the syntax, I can select Go. I then receive a message confirming that the change has been made, and when I check the table, it displays the updated values for the assigned columns alongside student 3. So that's how you update the information for one student. However, the update syntax can also be used to update the information for multiple students at once. Let's suppose that the college's engineering department has moved their classes to a new location on campus called the Harper Building, and I need to update the department's address on the table for all engineering students. I can perform this task using the update SQL syntax. The syntax is very similar to the previous example. First, I use the update clause followed by the name of the table. Then I add the set clause and state that I want to update the values within the college address column to Harper Building. So I type this as set college address equals Harper Building. Next, I type the where clause and state that I want this update to occur within the college address column for all students assigned the value of engineering in the department column. I then click Go to run the statement. Now, I just check that the table has updated the college address of the engineering department to Harper Building. I could also use the update statement to update multiple field values in multiple records. For example, I can return to the original SQL statement and add a new column value pairing to the set clause. If I want to update the home address column, I add a comma and write home address equals the new address information within quotes. Make sure to separate out the column value pairings with a comma. In this example, I'm updating 2 columns with one update statement. In this example, I'll demonstrate how to delete a single record from a table in a database. I'm using the student table from a college database and deleting the record of a student with the last name of Miller. I go to the SQL tab in PHPMyAdmin, and I write a delete statement beginning with the keywords delete from. Then I specify the table name as student table. I add a where clause and the condition to delete the data I want. I need the database to scan the list of students and identify the last name or value of Miller, and then delete that record from the table. So I type where, followed by last name, equal to Miller. I then run this statement by pressing the Go button. I get a confirmation that the record Miller has been deleted from the database. I can then access the student table on the left panel to ensure that the record or instance of Miller has been removed. Let's explore another example, this time by deleting multiple records from the student table. Now I want to delete the records for the 2 students within the engineering department. The beginning of the statement is the same as the previous example. I begin with the delete and from keywords, followed by the name of the table I'm working with, which is student table. The where clause is the key difference in this example. I type where, followed by department equal to engineering. This instructs SQL to identify all records that have a value of engineering within the department column and remove those rows from the table. But I need to be careful. If I don't correctly specify the where clause, then all the records in the table will be deleted. So now that I've completed my statement, I select Go to run it. I then check the table by clicking it on the left panel and confirm that the records for the 2 engineering students have been deleted from the table. Finally, let's quickly explore how to delete all records from a table. In this task, the syntax remains largely the same as in the previous examples. The key difference is that I remove the where clause so that now my syntax just states delete from student table. I remove the where clause so that now my syntax just states delete from student table. In other words, I'm instructing the database to remove all records from the student table. Then I click Go and confirm the deletion. Once the deletion has been confirmed, I check the student table, which is now empty. I now know that all records have been deleted.
You've reached the end of this module on databases and SQL. Nice work. You've emerged with a stronger understanding of what databases are and the value they bring when it comes to organizing and managing large amounts of data. You also became familiar with SQL as a language that allows you to interact with databases. It's a good time to recap the key concepts you've just learned about, so let's do that. In the first lesson, you were introduced to databases as a general concept. Following this lesson, you should now know how to describe how data is organized in a database, explain relationships between data in a database and why this is important for pulling meaningful information, and identify a few basic ways to express and present relational data. With this understanding of databases in mind, you then discovered how structured query language, or SQL, is used to interact with them. Specifically, you learned how to describe what SQL is and the operations that it is capable of, explain a use case in which these operations are used, use basic SQL syntax and commands, and create and drop a database. In the next lesson, you went more in-depth into tables and the role they play in databases. As a result, you should now be able to explain what tables are and how they are structured, identify the types of data that can be used in tables, create tables using the create table syntax, and restructure tables using the alter table syntax. The final lesson of this module focused on specific procedures for working with databases using SQL. The operations you should now know how to perform are using the insert statement, using the select statement, updating data, and deleting data. You now have a stronger grasp of databases and how you can access and manipulate the data they hold in order to best meet your needs. Next, you'll learn more about some of the tools that are specific to working with data in React Native. Previously, you learned how to store data in databases. Databases are great if you want to query and manipulate the data. However, they add complexity to your project. What if you only wanted to persist the data as it is presently for later reading? Android offers a simpler solution for this type of storage. It is called shared preferences. In this video, you will learn what shared preferences is and how it can help you persist data. Mario and Adrian want to make the Little Lemon Android app friendlier. To achieve this, they want to ask the user for their name if they haven't provided it yet. Once the user provides their name, the app should welcome them by using their name every time they return. Android provides a solution for storing simple types of data, including booleans, numbers, strings, and string sets. Shared Preferences is a file storage interface that can be accessed from anywhere in your app where you have an Android context reference. Shared Preferences is ideal for persisting simple data that you only want to store as is, such as the name of the user, the last time the app was started, or user settings like a receive notifications preference. Thanks to Shared Preferences, support of strings, and your knowledge of JSON, you can persist more complex data structures as well. All you have to do is convert the data to JSON before persisting it and convert it back when you want to read it. To use Shared Preferences in your app, you must first obtain an instance of it. You obtain an instance of Shared Preferences by calling getSharedPreferences on any Android context, such as the application, an activity, or a service. This function takes 2 arguments, the name of the file that stores the preferences and an operating mode flag. The first can be any valid file name, and the second is commonly set to 0 or context mode private, which means the file can only be accessed by applications sharing the same user ID as the current app. Other modes allow read or write access to all apps. You can also obtain the default shared preferences instance for your app by calling preferencemanager.getDefaultSharedPreferences, passing in any Android context. Once you obtain an instance of shared preferences, you can start writing data to it. Data is written using an editor. The editor is responsible for saving any changes you make to the shared preferences file atomically. To get an instance of the editor, you call the edit function of the shared preferences instance you have. The editor exposes a few functions for storing data. Every data type has its own function, including putBoolean, putInt, and putString, and others. Each function takes a unique key as a string and a value to persist. You can keep calling these functions until all the data you want to persist is added to the editor. You can remove values from shared preferences by calling remove, passing in the unique key of the value to remove. You can also remove all values by calling clear. To persist the changes in the editor, you call commit or apply. Commit is synchronous and returns a Boolean indicating success or failure. Apply runs asynchronously and safely saves the changes in the background. You will not be notified if apply failed. If the shared preferences file did not exist prior to calling commit or apply, it will be created when these functions execute. Shared preferences offers multiple functions for reading stored values. These include getBoolean, getString, getInt, and others. Each function takes the unique key used to save the value originally and a default value, which will be returned if no stored value was found. Shared preferences offers a getAll function that returns a map of all stored keys and their values. It also offers a contains function, which tells you whether a value is stored for a given key. Finally, shared preferences allows registering and unregistering listeners for changes. Let's look back to the Little Lemon app upgrade. To implement the requested features, asking the user for their name and using their name to welcome them each time they return, you would first obtain a copy of shared preferences. This can be done from anywhere in your main activity by calling val shared preferences equal to preferencemanager.getDefaultSharedPreferences this. You can then check if the user previously provided a name by calling shared preferences.containsName. If a name exists, you can obtain it by calling shared preferences.getStringName and present the user with a personalized greeting. If a name does not exist, you can ask the user for their name. Then you can save their name using shared preferences.edit.putStringName, name apply. In this video, you learned how shared preferences can be used to persist and restore data. Working with shared preferences will be a common activity in your career as you work with data in Android development. In this video, you will learn how to use shared preferences to persist and restore data. Adrian wants to know how many times users entered the Little Lemon app. For this purpose, you need to increment a counter every time the app is started. So let's find out how to get that done. Every time a user enters the app, they trigger the onStart function of the main activity. This is the perfect place to perform the count. I start by obtaining a reference to the shared preferences instance named Little Lemon, then assign it to shared preferences variable. Now I read the current count int value from shared preferences. It will be stored under the key start count. If the value isn't present, the default count should be 0. Assign the value to a variable named last count. I continue to declare new count, a variable with a value of last count plus 1. Now to output the new value to logcat using the Android log.d function. I set the tag to start count and the message to new count, followed by the count. Next, I obtain a shared preferences editor by calling the edit function. I continue to call putInt, passing in start count as the key and the new count variable as the value. Then I commit the change by calling the apply function. To test the implementation, I launch the app and search logcat for the start count log. It should say new count 1. Now close the app and start it again. Observe logcat printing out new count 2. You have successfully read and persisted a value using shared preferences. In this video, you have learned how to read values from shared preferences. You have also learned how to persist values to shared preferences. You will find using shared preferences is an easy way to persist data which you will often turn to in your career as an Android developer. In this video, you will learn how to connect the user interface or UI state to shared preferences. Adrian wants the Little Lemon app to allow users to toggle between breakfast and lunch menus. To test this idea, he wants a switch that will toggle the title of the menu between breakfast menu and lunch menu. The menu title will be set based on a shared preferences Boolean flag controlled by the switch. In that way, state is persisted across app launches. I'll open a starter project located in the C7 M4 L1 item 4 connecting shared preferences to state starter project zip file. Then start by creating a composable called title that sets the menu title based on a Boolean flag called show lunch menu. If the flag is true, this composable will display the title of the menu as lunch menu. Otherwise, it will display the alternative breakfast menu title. Next, I add a lazy shared preferences reference called shared preferences to the main activity. The instance is obtained by calling getSharedPreferences with a Little Lemon string and mode_private as arguments. I create show lunch menu live data to store values from shared preferences. I then define shared preferences listener to observe value changes in shared preferences and pass newly obtained value to the show lunch menu live data. When the activity is created, the title should update. I'll begin that process by reading the Boolean value for the lunch menu key from shared preferences with a default value of false. I can do this by calling sharedpreferences.getBoolean with lunch menu and false as arguments. The value is assigned to a show lunch menu live data variable. Next, I will register shared preferences listener that was defined earlier. I will create the selected variable inside column and observe show lunch menu live data as state. I set an initial value using the value retrieved from shared preference. Next, to add a switch composable. To persist the switch state, I call edit on shared preferences with commit equals true as an argument. Following up with a call to put Boolean, passing in lunch menu as the preference key and it as the value. Finally, I add the title composable defined earlier and pass the selected value. Now when I run the app, observe the title saying breakfast menu by default. When I tap the switch, observe the title changing to lunch menu. Close the app, launch it again. Now the title shows lunch menu. That demonstrates that I have successfully persisted the title state. In this video, you learned how to bind a persisted state from shared preferences to the Android app UI. In a previous lesson, you learned how to persist data in shared preferences. Shared preferences is a great solution for storing simple data to be retrieved just as it is. But what if you wanted to persist more complex data and only query some of it at a time? In a previous week's learning, you learned about structured query language, or SQL. You learned how it can be used to query data stored in a relational database. SQL is a perfect solution for this problem. However, SQL is only a language. It needs an engine to run it. Queries need to be processed, tables need to be stored. Android comes with such a built-in lightweight engine, SQLite. In this video, you will learn what SQLite is and how you can use it to persist and query data. Mario and Adrian want to update the Little Lemon Android app with a search functionality. They want users to be able to search their menus for any dish by its name. Users will type in their search query and the app will list all the matching dishes. In SQLite, Android provides a built-in solution for storing and querying data in SQL tables using SQL statements. SQLite is a small, fast, full-featured SQL database engine. It is written in C and it is open source and free for anyone to use for any purpose. SQLite is perfect for when you want to persist complex data which you later want to query. Because it works with SQL statements, it allows you to easily persist, update, delete, or read data. In fact, SQLite is so useful that, according to the SQLite website, there are currently over 1 trillion SQLite databases in active use. You will find many opportunities to use SQLite. For example, you may query an API for data. The API may be expensive or it may not work well under heavy load. In these cases, you may choose to persist the data returned from the API locally. If you store the data using SQLite, you can easily query it for slices of the data that you're interested in. Another example could be that you have rich data bundled in your app in a comma-separated or JSON format that takes a long time to parse. To load the app faster after you parse the data for the first time, you can choose to persist the parsed data in SQLite. Loading the data in subsequent runs from SQLite will be much faster. You can even bundle the data as a SQLite database file and avoid this initial parsing as well. You can also use SQLite to manage rich data locally without API support. It can be used to store inventory, contacts, or any other collection of elements. You can then query, sort, and paginate through the data using SQL statements. In this video, you learned about SQLite and how it can help you persist complex data and query it. Previously, you learned that the default database in Android is SQLite, and you also learned and practiced how to write and run queries in SQL. While it is vital to have that knowledge, it often becomes cumbersome to write queries because writing queries is prone to human error, like typos, and as a result, the query can be syntactically wrong. There is no compile time validation of the queries, and that may lead to issues at runtime. To overcome such issues, Android Jetpack introduced the Room Data Persistence Library. In this video, you will briefly learn about what Room is and observe how to set up the Room library to work with SQLite databases in Android. The Room library is an abstraction layer and acts as a wrapper built over SQLite that allows database access. The benefits of Room include that it provides compile time safety, that is, the syntax of queries is validated at compilation time. It reduces the error-prone boilerplate code that needs to be written to define and run queries, especially by providing concise syntax for common processes such as CRUD operations. For such reasons, the official Android documentation does recommend using Room over using SQLite APIs directly. Now, let's demonstrate how to set up Room in your Android application. First, I create a new Android application project with an empty activity project and name it Room Setup. Then, I open the build.gradle file in the app module and ensure that the capped annotation processor is applied to the plugins as plugins and with an ID of Kotlin capped. You don't need to understand annotation processors in depth at this moment, but it's important to know that annotations are part of code and are prefixed with the @ sign, for instance, @insert, @delete, and so forth. Annotations convey special meaning to the compiler. The capped plugin helps to process such annotations to generate code at compile time. Then I add these lines to the dependencies block to use Room with the app module. When this demonstration was created, the latest version of Room is 2.4.3. That is why those numbers appear here in the code. If newer versions of the library are released, the version number will change, and you would need to insert that new version number. Now that we have set up the dependencies for the Room library, let's check out its 3 major components. The first one is the database class. This holds the reference to the SQLite database and serves as the main access point for the underlying connection to your app's persisted data. Second is entities, and this represents tables in the database. Finally, data access objects, or DAOs, provide methods that your app can use to query, update, insert, and delete data in the database. Now, let's have a quick walkthrough of a sample implementation for these components with Room. This is just a brief overview, and these concepts will be explained in later sections of this course. This is an entity that represents a table containing the information for the players of a sports team. Here's a DAO that contains operations such as adding a player, deleting a player, or getting the list of all players. This definition of the room's database class provides the connection to the underlying app's database. Finally, you use an instance of the database class to access the database access object, which in turn is used to perform various operations on the entity. You will learn about these components in more detail in the upcoming sections of the course. In this video, you learned how to set up the Room Persistence library in Android and had a brief overview of its major components. Room is one of the most popular Jetpack libraries, and being able to use it is vital to your work with SQLite databases in Android. In this video, you will learn how to connect the user interface state to a Room database. Little Lemon started working on an app called Lemon Inventory to manage their stock. So far, I've added an inventory list and inventory item composables. The inventory list composable displays the list for inventory items. Each inventory item presents an item name, its current quantity, and 2 buttons to increase or decrease the inventory by 1. I will now add what the app is missing, which is code to read data from a Room database, bind the data to the screen, and update the Room database data. I start by annotating the item model with entity so it can be used as a Room model. The ID field is a unique identifier of each item and should be annotated with primary key. Next, I create the Data Access Object, or DAO. I declare an interface called Inventory DAO and annotate it with DAO. I will add a getAllItems function, annotated with a query with a value of select all from item and order by name. It returns a live data of a list of type item. Next, I add an updated item function having one parameter named item of type item. Now I continue to implement the Inventory Database Abstract class, which extends the Room Database Abstract class. I annotated with database, setting the entities to item class and the version to 1. The database needs one abstract function called Inventory DAO, which returns an Inventory DAO. I now create Inventory Repository. It is a class with a single constructor parameter, context of type context. I declare a private database field and assign a Room database to it by calling Database Builder with the application context, the Java class of Inventory Database, and inventory.db as the file name. I call createFromAsset with database/inventory.db to initialize the database with the bundled inventory.db file. Then I call build to construct the database. Now to add a function called getAllItems. It returns database.inventory.dao .getAllItems . Also, I add a function called updateItem with one parameter, item of type item, which returns database.inventory.dao .updateItem open parenthesis item close parenthesis. At the top of the main activity, I declare an inventory repository field using lazy delegate and pass this as an argument. Inside the surface block, I define onUpdateItem variable and a store lambda that will update item in the database when the listener will be executed. I call runBlocking with IO as an argument to perform the update on a background thread. I call inventory repository.getAllItems parentheses .observe as state open parenthesis empty list parentheses close parenthesis and assign the result to the items variable. Finally, I add inventory list and pass items to display them on the screen. I will also pass onUpdateItem as the listener, so the composable could trigger updating the item in the database. Now when I run the app, observe the list of inventory items displayed. When I tap the plus and minus buttons of some of the items, observe the inventory count is updating. I will close the app. Launch the app again. Now the inventory count is persisted. In this video, you have learned how to display data persisted in the Room database. You also learned how to update the database data in response to user interaction. That's the end of this week's learning where you explored SQL data in Android. Well done! In this week, you learned how shared preferences can be used to persist and restore data. In addition, you learned about SQLite and how it can help you persist complex data and query it. Shared preferences can persist many different types of data, like usernames, the time when the app was last started, or other settings such as a receive notifications preference. You can also persist more complex data by converting the data to JSON before persisting it and converting it back for reading. You worked with shared preferences to implement a Little Lemon app upgrade example, asking a user for their name and using their name as part of a welcome message. This included the way to check and obtain a username in the app or requesting and saving the name using shared preferences. You also experienced connecting shared preferences to view state and read and writing data with shared preferences. Android provides SQLite as a built-in solution for storing and querying data in SQL tables using SQL statements. You again saw how to persist complex data which you later want to query, but this time using SQLite. SQLite can allow you to persist the data returned from the API locally. Because it works with SQL statements, it allows you to easily persist, update, delete, or read data. SQLite can also manage rich data locally without API support, where you can then query, sort, and paginate through the data using SQL statements. To properly work with data in SQLite, you practiced setting up room and connected room to view state. Then you could run queries and read and write using room. That ends your study for this week, during which you worked with data in Android by using shared preferences and SQLite. You've reached the end of this course about working with data in Android. Well done! You did a lot of work, learned new skills, discovered some development tools, and expanded your understanding of how to integrate your app with data sources. Take a moment to congratulate yourself and reflect on all you have learned in this course. This end-of-course graded assessment week features a final project where you will get a chance to apply what you've learned in a development environment. There you will get JSON data from a REST endpoint, implement a REST API query, and convert the JSON response, storing it in SQLite. You'll also display data as a list in the app and implement filtering and sorting of the data to allow users search a food menu in the app. But before you embark on the final project and assessment, let's reflect on the key learning milestones you have reached. You began this course with an introduction to REST APIs, and you got to know about RESTful API in Android development. You had a quick summary of what HTTP and HTTPS are and how they relate to Android development. For instance, exploring how HTTPS communication requires a client requesting information and a server that responds to the request to serve the content for your app. That included knowing about methods such as get, post, put, patch, and delete. REST is an architectural style for designing APIs for a project. You can only say that an API is RESTful if its constraints are met. You recapped on important areas such as REST best practices, security, authentication, authorization, and access control. That got you covered for most of the API concepts and the core details of REST APIs. While working with HTTP in Kotlin, the major items you covered included knowing how KTOR is used to process requests and responses synchronously and asynchronously, sending and receiving JSON in Kotlin, practicing how to fetch image URLs and display dynamically in the app, and you learned about querying a REST API with JSON as the data format. Following an introduction to databases and SQL, you could, for instance, load database data into the Little Lemon app to display menu information. You learned about the concepts of data and databases, including how data is related in a database and different database structures and their uses. You then progress to learn about more advanced database techniques and practice performing create, read, update, and delete operations in an app, and use SQL operators to sort and filter data. To complete your work with SQL data in Android, you operated with the alternative data techniques of shared preferences and SQLite. Using either shared preferences or SQLite, you examined how to persist simple and complex data which you can later query. For instance, you can use such an approach to ask a Little Lemon app user for their name and use it as part of a welcome message. Shared preferences could persist different types of simple data like usernames, the app startup time, or other settings such as a receive notification preference. With SQLite, you can persist the data returned from an API locally. Working with SQL statements, SQLite can persist, update, delete, or read data. To properly work with data in SQLite, you practice setting up room and connected room to state. When that setup was completed, you could then run queries and read and write using room. Well done. You have covered many concepts and skills and gained significant Android mobile app development knowledge during this course. Best of luck as you try out all these approaches to working with data for your app. Congratulations on reaching the end of this Working with Data in Android course in the Android Developer track. You've worked hard to get here and developed a lot of new skills along the way. You're on the way to becoming a valued developer of great Android apps. You should now understand more about how Android applications communicate over the web, including being able to apply asynchronous programming techniques using Kotlin and demonstrate a working knowledge of SQL. For instance, being able to store app data using SQLite. The key skills measured in the final project and the graded assessment quiz revealed your ability to develop using RESTful API, apply asynchronous programming techniques to query REST APIs and handle their responses using Kotlin and Android. Operate the syntax rules of SQL using common SQL commands to work with SQL data in Android. And finally, to be able to read, write, or query data using shared preference and SQLite. You might be thinking about the next learning steps you should take. This Android data course has enhanced your app development knowledge and skills in several key areas. With coding and development, there is nearly always something more to learn. So, if you found this course helpful and want to discover more, then why not register for another course and continue your learning journey? You'll continue to develop your skill set during each of the Android developer courses. When you complete all the courses, including the capstone project, you'll receive a certificate for Android mobile development. Depending on your goals, you may choose to delve deeper into your chosen area with advanced role-based learning or take other fundamental courses once you earn this certificate. Whether you're just starting out as a programming professional, a student, or a business user, each course end project proves your knowledge of Android development. These projects and certifications provide you with evidence that you can use to authenticate your technical skills. Thank you. It's been a pleasure to embark on this journey of discovery with you. Best of luck in your future learning and career.